Okay, if you recall, we covered this problem in class where we were looking at the universal energy equation, and we were talking about conservation of energy. So this is the Wiley Coyote problem. We've worked it in class, but I'd like you to be able to step your way through this and understand every part of it in case you see something like this again on a test. Okay, so we started off, and the easy question, I suppose, was to find the gravitational potential of the anvil that was 1,000 feet above on a cliff that the Roadrunner was going to drop. Okay, so what we know is the formula for potential energy. Over here I have a picture to draw. All right, so here's the cliff, here's the anvil at the top of the cliff, and what we have in this situation is the energy at time 1 is the potential energy at time 1 plus the kinetic energy at time 1. But since the anvil is not moving, the kinetic energy at time 1 is 0. Okay, so the potential energy, on the other hand, we can calculate that because we know that the anvil is at a height of h. Okay, so the kinetic energy is 0. And what is the potential energy? So what we know is that for potential energy, it's mass times the gravity times the height. All right, so then we check when we start to plug into this, what are our units? We look at kilograms here, we're looking at meters per second squared here, and then we need to make this conversion to get the 1,000 feet into meters. Okay, so I have that one done as well, so let me zoom in on that. All right, so what we know is if we have a height of 1,000 feet, we need to convert that into meters. Okay, so I'm thinking, I know my conversion factors. In 1 foot there's 12 inches, there's 2.54 centimeters in 1 inch, so I line these up to where they cancel, and then there's 1,000 centimeters in 1 meter. Okay, so everything seems to line up, and I end up with the height being 304.8 meters. All right, so that lets me plug this back in. I take the 1,000, I know that's already in. Remember, this is the MKS system. What we need for units are kilograms, meters, and seconds. Okay, so then 9.8 meters per second squared, that's gravity. And then we just found this number, 304.8 meters. So we plug all that in, and you can check this on your calculator. You get 299 kilojoules. All right. So then in part B, we're wondering what is the speed of the anvil when it hits the ground. Okay, so that's the second time that we are looking at, time 2. So we drop the anvil, and then we're looking at it right before it hits the ground. So remember, there's always this trade-off between potential energy and kinetic energy. So I'm going to call this E2 is equal to PE2 plus K kinetic energy 2. All right, so let me erase this line. All right, so that's what we know. At the second time, the energy is conserved between time 1 and time 2. All right, so the thing is, the potential energy, the height now, is equal to 0 because we're getting this right before it hits the ground. So that means the potential energy is equal to 0. All right, since energy is conserved, I know that the energy at time 1, 299K, which was the potential energy plus the kinetic energy at time 1. Remember, the kinetic energy at time 1, this is not moving, so the kinetic energy is 0. All right, so that potential energy matches between 2 times. That's what we're talking about, conservation of energy. So that would equal to PE2 plus KE2, but PE2 is 0 because the anvil head is at 0 height. So that leaves us with just KE2. All right, so that's nice because now we know that the kinetic energy is 299 kilojoules. All right, so from there, it's just a matter of solving for the velocity. Okay, so I know the kinetic energy equation is 1/2 mv squared, so I plug in the things I need. This is already in joules. This is in kilograms. So I solve for velocity. Now, using a consistent system of units, what I know is that the velocity is going to be in meters per second. All right. So if you carefully read the problem, it says, what is the speed of the anvil when it hits the ground? Well, meters per second is a speed. And so on an exam, I would have stopped right there. Of course, I could have asked you, what is the velocity of the anvil in miles per hour? And we would just do the usual conversion step. So we're looking at meters per second, and then we convert this all the way across where we're looking to end up in miles per hour. So in 1 meter, 100 centimeters, 2.54 centimeters in 1 inch, 12 inches, 1 foot, and 5,280 feet in 1 mile. Okay, so these are just conversion factors that I already had memorized. On an exam, I would give you a table of conversion factors that you could use. Okay, so I do this calculation, and what I get is 173 miles per hour. All right, so hopefully you can step through this and understand all the steps in this calculation.